Conservative vector fields, Part 1. We will start with some definitions. Suppose a curve C in either 2 or 3-dimensional space is described parametrically by a position vector r of t, where t runs between A and B. We say that the curve is closed if r of A equals r of B, meaning the curve starts and ends at the same position. If a position on the curve is never repeated, we say the curve is simple. An open region R is connected if it is possible to connect any 2 points of R by a continuous curve lying in the region. The region is simply connected if every closed simple curve in the region can be deformed and contracted to a point. Previously, we found that for this particular vector field, the line integral from P to Q via the quarter circle and the line integral from P to Q via 2 line segments is equal. This brought up the question, for what vector fields are the values of a line integral independent of path? This question involves conservative vector fields. So let's define a conservative vector field. A vector field is said to be conservative if there exists a scalar function phi such that the vector field is the gradient of phi. So if the vector field has the components f, g, h, that would mean that f equals phi partial x, g equals phi partial y, and h equals phi partial z. If f has continuous first partial derivatives, then phi has continuous second partial derivatives. Now that means that the order of differentiation in the second partial derivative of phi does not matter. Now this leads to interesting consequences regarding the vector field f. Let f be defined on a connected and simply connected region in 3-dimensional space, where f, g, and h have continuous first partial derivatives. Then f is conservative if and only if these partials are equal. If f is in 2-dimensional space, we only need to check one equality, that f of y equals g of x. Let's determine whether this vector field is a conservative vector field in 2-dimensional space. For a vector in 2-dimensional space to be conservative, we need only check that f partial y equals g partial x. Since f partial y does equal g partial x, we conclude that the vector field f is conservative. Determine whether this vector field in 3-dimensional space is conservative. Here we have to check 3 conditions because we're in 3-dimensional space. So we need to check that f partial y equals g partial x, f partial z equals h partial x, and g partial z equals h partial y. So check all of that. That's a lot of partials to check. Taking the partials, this is what we get. And since the partials have that the right things are equal, we can conclude that the vector field is conservative. Now, we'll take this subject up again in part 2. So I'll see you then.